Hi, and welcome to our first lesson on the graphs of rational functions. We'll be spending about 3 days on this topic. Functions who, like these, have their variables on the bottom. The two basic setups for rational functions: 1 over x, so this would be an odd exponent. Notice the graph is in two pieces, and its normal orientation is in the first and third quadrants. So if we happen to have a negative 1 over x, things would reflect over the x-axis because that's how functions work. This one is in two pieces. I often call this one the butterfly, although I've heard other names for this as well, but that's what it reminds me of. This one, 1 over x squared, so over an even exponent. This one to me looks like a volcano. The graph is still in two pieces. First and second quadrants is the normal location for it. I'd like to have you think about the end behavior on these functions. End behaviors happen when x gets extremely small or extremely big. So I'd like to have you think about that. As x gets very, very, very small, what is happening to y? Getting closer and closer to 0. Can't quite get there. Really tries hard. Same thing is true in the other direction. As x approaches positive infinity, y also decreases towards 0. Now, the same thing is true here. The location of the branch is different, but still this rational function, when x gets really small or really big, is going towards 0. So let's get those end behaviors for the squared one out there. And that's going to be important for us to remember all through this lesson. The end behaviors on a 1 over x function, a rational function, it's heading towards 0. Many rational functions have asymptotes, and these two that you're looking at do have asymptotes. Sometimes I call those lines of avoidance. Pretty descriptive. Again, the function tries and tries and tries to get at an x of exactly 0. It just cannot seem to get there. It avoids that spot. The same thing is true of y equals 0 in this one. So this function has a horizontal asymptote at 0 and a vertical asymptote at 0. Same thing here. Today and tomorrow we're going to learn how to find 3 types of asymptotes. You've already talked about 2 of them, vertical and horizontal. And that's going to be our focus today. Tomorrow we'll talk about slant asymptotes, but today our focus is going to be on vertical and horizontal asymptotes. Vertical asymptotes, folks, they happen when, and I've got a sentence here, when there's an x value that makes the denominator 0 and that cannot be factored out. That last criteria is sort of important. An x value that makes the denominator 0 and that cannot be factored out. If that is the case, then what you'll notice is that y approaches infinity from one side of the avoided x value, and it approaches negative infinity from the other side. If you think back to the shapes of the 1 over x and 1 over x squared, well, 1 over x, I guess, is what we want to talk about. Y approaches positive infinity there, negative infinity there. All right, to find vertical asymptotes then, we need to find values of x that make denominators 0. In the first one, it is clear to see that it will have a vertical asymptote at, well, to make that 0, x minus 2 would have to equal 0, so x would have to be 2. Most of us won't need to show the subtraction. Will you do the same thing for me here? Pause the video, find that vertical asymptote. Good. The only value that will make this equal to 0 is negative 6. So this function will have a vertical asymptote at negative 6. The last one I saved because I wanted to show you something. You might say, well, this one will have a vertical asymptote at x equals 3. But I would say this is why we had to put that business in there about what can't be factored out. The top of this factors, you can do the X box, or if you just think about it, things that multiply to make 3 but add to make -4, that factors into x minus 3 times x minus 1. And that means that we have what's called a factorable discontinuity or removable discontinuity. That is, that term that creates the problem factors out. This is called a removable discontinuity. And a better name for it might be a hole. See, what happens with this function is that it acts like the line x minus 1 in every single value. So x minus 1, y-intercept down here. For every single x, it acts like that line, except when x is equal to 3. So those two are points on that line, but when x is equal to 3, this function is not defined. That is, it works for every x except x equals 3. And that happens when there is a removable discontinuity or a factorable discontinuity. It's so that, I guess, what we're trying to say, be careful. Factor. Factor before you judge whether or not there are vertical asymptotes. Very good. Horizontal asymptotes, they can happen when the degree on the numerator is less than or equal to the degree on the denominator. So the degree on the numerator here is 1. It's the same as the degree on the denominator. This will have a horizontal asymptote. If there is a horizontal asymptote, what you'll see is that x approaches positive infinity on one side of the avoided y, and it approaches negative infinity on the other side of the avoided y. Again, if you think about the graph of 1 over x, the horizontal asymptote, x approaches infinity on one side of the avoided y, and negative infinity on the other. The avoided y here would be y equals 0. Alright, the method for finding horizontal asymptotes is a little bit different. You divide, it says, and this is the mathematical process, you divide each term by the highest power of x in the denominator, and then determine what will happen to each term as x approaches infinity or negative infinity. I want to take a second and go through that with you here. If we're going to talk about horizontal asymptotes for this function, it says divide everywhere by the highest power of x in the denominator, and that is just plain old x. Divide every single term. Now, we can do a little bit of arithmetic here. X over x, or any number over itself, is 1. So we have 1 on top over 1 minus 1 over x. But then it says, and this is important, that we determine what will happen to each term when x goes toward infinity or negative infinity. Nothing changes with 1. However, we will remember, I hope, in 1 over x, which is what we have right here, when x gets really, really big or really, really small, that's going towards 0. And so what happens here, the net effect of this is as that becomes 0, the horizontal asymptote will be what's left over, 1 over 1 minus 0, or just 1. This one has a horizontal asymptote at y equals 1. Alright, I want to have you try that process here. First of all, we're going to check to see if there is a horizontal asymptote. The degree on top is 1 less than the degree on the bottom, so we are going to have an asymptote. It's less than or equal to the degree on the bottom. Divide everywhere by the highest power of x in the denominator. Simplify. So let's see, this would be, I'm going to come over here, 2 over x on top over 1 plus 8 over x to the third. Ladies and gentlemen, the truth of the matter is, if 1 over x goes to 0, so does 2 over x. When you're talking infinity, that little change of 1 on top doesn't mean anything. So this is acting just like 1 over x, and that's going towards 0. On the bottom of this fraction, nothing changes with 1. When x gets really big or really small, 1 is 1. But when x gets really big or really small, 8 over x cubed, you guys, if 1 over x goes to 0, then this just gets there faster. So what shakes out in this one is that the horizontal asymptote will happen when y is equal to, on top we had 0, and on the bottom we had 1. So this will have a horizontal asymptote at y equals 0. Very good. The next one I'd like you to consider would ask you if this one has a horizontal asymptote, and you will check and say the degree of the numerator is not less. No horizontal asymptote here. So this was the trick question. One of our goals today is to use those asymptotes to help you graph functions. So we're going to ask you to take a look at, first of all, this function. There are 1, 2, 3 questions here. Find the vertical and or horizontal asymptotes and then sketch the graph. Alright, I'm going to have you pause the video. I want you to find the vertical and horizontal asymptotes if they exist. Okay, I have a vertical asymptote at x equals 5. That's what will make the denominator 0, and it does not factor out in any way, shape, or form from the numerator. A horizontal asymptote will happen at y equals 1. Again, you had x on top, x on the bottom, so you divide everywhere by x. The 5 over x term goes to 0, and then these are both 1. So, ladies and gentlemen, what you have there is a framework for your graph. Let's sketch those asymptotes in. There's x equals 5. Here is y equals 1. So in essence, folks, our graph, instead of being centered around the origin, is going to be centered around here. Now, I'm not exactly sure what the shape is. I'm going to either look at a calculator table or build a little table of my own. When x is 6, this would be 6 over 1. So when x is 6, y is 6. That's up here. When x is 7, 7 over 2, that's 3.5, so it's dropping. This branch is in that place. Okay, I only plotted a couple of points, but I know that that's enough to get me the shape. Now I'm going to do the same thing here. When x is 4, we're talking about 4 over, it would be -1. So, well, when x is 4, y is -4, so down in here. When x is 3, that would be 3 over -2, so 3 and -3/2 around in here. We're looking at the other branch of this in here. Now you can verify that on your calculator, but really just plotting a few points is enough to know. You know that it's going to be 2 pieces because it is a rational function. Let's do the same thing here. This function is x cubed. That may make the top behave a little bit differently. Over x minus 2 times x plus 1. Vertical asymptotes and horizontal asymptotes. Stop the video and find those. The degree on top is bigger than the degree on the bottom. This does not then, because the degree on the bottom would be 2 powers of x. No horizontal asymptote. Vertical asymptotes will happen at 2 and at -1. So let's sketch those in. Those are our vertical lines of avoidance. And I have got to tell you the truth, I don't know on this one. I'm not sure what it's going to look like. So I am going to bring my calculator up. I have both functions in my calculator. I just want to take a quick look at this first one and make sure that we got that graph right. And there it is. Looks like we did a pretty good job with that one. I'm going to go back to my y equals, and I'm going to shut this one off and look at the second, because I really don't have a good idea of what that x cubed on the top is going to do. So I'm looking at it in a Zoom 6 window, and I'm going to just do this. I'm going to sketch. I know that this is not exact, but if we're asked to sketch a graph, as long as we have a good framework drawn and a decent picture of what's happening, this would be considered a good sketch in my opinion. Okay, the framework is what's important to me, knowing about what those asymptotes do, and then we just kind of hang our function around it. The last of our example problems shows us a transformation of the function, the rational function, y equals 1 over x. I would like to know the equation of this function. So I need to have you look at how it's been changed in the coordinate plane and incorporate those changes into a function rule for this. Alright, let's pause the video and do that. Okay, here's my thinking. I kind of sketched in the crosshair on this one, and it looks like it's been moved left 2 and down 2 to incorporate that into my function rule. The left or right movement is right in there with the value of the variable. So, and it goes the opposite of what you'd expect. 1 over x plus 2. And then down 2, that's just a minus 2 added onto the end of the function. So that's our lesson for today. I'm going to expect lots of questions tomorrow, and we'll see you in school.